Hello everyone, welcome to my class. In today's class I am going to cover partial derivatives. So let me start the class right away. We have a function of two variables f and its graph, that is a surface given by z equals to fxy, and wish to ask the following questions to ourselves. What is the steepness of the surface at a point in any directions? So in these sections we study how to find the steepness of the surface in the particular x directions and in y directions. First, let me find the steepness of the surface in x directions. So first let me talk how to find the slope or steepness of the surface in x direction. So in the diagram, here is a point AB in the domain of f of xy, and the surface is up here, which equation is z equals to f of xy. I think you are familiar with this diagram. It means the surface diagram here. So pick a straight line through AB parallel to x-axis in the xy plane and extend that line vertically into a plane y equals to b. Now this is a y equals to b plane. Then this plane intersects the surface at this curve. Let's say this curve is z equals to f of x b, because y is fixed b. So now let's focus on z equals to f of x b, this red curve. Then we have this z is function of x only, so now it's a function of single variable. Then we can use the calculus 1 language to find the derivatives. So by calculus 1, the slope of the curve z equals to f of x b in x direction is simply the regular derivatives, dz over dx equals to d over dx of f of x b, and evaluate at x equals to a, and we denote this derivative by this notation here, f, this is the derivative with respect to x, keeping y constant, and evaluate at ab, where this we also call fx. Now this fx ab is called the partial derivative of f with respect to x, keeping y variable constant, and evaluate at the point ab. I hope this notation makes sense to you all. So then we found the derivatives of these functions or of this curve z equals to fx b in x directions. So this means we found the steepness, or we found the rate of change of fxy in x directions. I hope this makes sense to you. Now similarly we can find the steepness of the surface in y directions. That means the partial derivatives of f with respect to y, keeping x as constant at point AB. Notations. The partial derivatives of f with respect to x are denoted with these notations, and partial derivatives of f with respect to y is denoted by these notations. Awesome. Quick note, the partial derivative gives the slope of the tangent to a trace of the surface at a particular directions. All rules of calculus 1 derivatives can be used to compute the partial derivatives, just replacing regular d by curvy d. So we have this curvy d notations here. So please make sure where to use this curvy d and the regular d. If you have a function of single variable, we use regular d. If you have a function of more than one variables, then we use curvy d for the partial derivatives. Great. So now let's move on. Second partial derivatives, that means the partial derivatives of the first partial derivatives, which are here. So these are our first partial derivatives, del f by del x and del f by del y. Now let's take the partial derivatives of del f by del x with respect to x and with respect to y. With respect to x gives us del square f over del x square or fxx, and partial derivatives of del f by del x with respect to y gives us here fxy, and similarly the partial derivatives of del f by del y with respect to y and with respect to x. So fxx, fyy, fyx, and fxy. So we have 4 second partial derivatives. Great. Let's move on. Clairaut's theorem. The mixed partial derivatives fxy and fix are equal if and only if the mixed partial derivatives are continuous at every point in their domain of definition. Laplace equations. The partial differential equations del square u over del x square plus del square u over del y square equals to 0 is called the Laplace equations, and its solution is called the harmonic functions. Great. Quick remark. In calculus 1 we studied the derivative implies continuity of functions, but the existence of partial derivatives do not guarantee the continuity of functions. A lot. We know dy by dx equals to 1 over its reciprocal, but this is not true in the partial derivatives case. Now with these ideas, now let's do some example. First example, consider f equals to x to the 4 plus 5xy cubed plus yex plus x sine y, and answer the questions A and B. So part A, find the first partial derivatives of the functions f. So first partial derivatives means fx and fy. So let's compute the first partial derivatives of f. So let's compute f of x. That means the partial derivatives of f with respect to x, keeping y constant. So here 4x cubed plus the y cubed is constant, so 5 times y cubed, 5y cubed, plus y constant, so y as it is, then derivative of e to the x with respect to x becomes e to the x itself, and the plus sine y is constant, derivative of x with respect to x is 1, so simply sine y. So we're done. Similarly, the partial derivatives of f with respect to y, so keep x constant, so x to the power 4 is constant, so this becomes 0. Similarly, 5x is constant, y cubed becomes 3y squared, so 3 times 5 is 15 xy squared. Next, we are taking partial derivative with respect to y, so e to the x is constant as it is. Partial derivatives of y with respect to y is 1, so simply ex. Similarly, x constant, partial derivative of y with respect to, similarly, x constant, partial derivative of sine y with respect to y is cosine y. I hope this makes sense to you all. Part B, find the second partial derivatives of the functions. So now we need to find out fxx, fxy, fyy, fyx. So now fxx, that means let's take the partial derivatives of fx with respect to x. Again, keep y constant. So here is 12x squared. This term is constant for x partial derivatives, so 0. Yex, sine y again constant 0. So fxx is simply 12x squared plus yex. I hope this makes sense to you here. It's slightly confusing in the first time, because here when you take a partial derivatives with respect to x, keeping the y variable constant, and vice versa. Similarly, let's talk about fxy, means let's take the partial derivatives of fx with respect to y. That means x is constant, so fx cubed is constant, so 0. Then this is 15y squared plus ex plus cosine y. Similarly, let's take the partial derivatives of fy with respect to x. So here 0, 0, this is 15y square ex plus cosine y, keep x variable constant, and similarly we can find fyy. Awesome. I hope this computation makes sense to you all. Now let's move on. Example 2. Find all the first and second partial derivatives of functions e to the power x plus y. Solutions. We can rewrite our function as ex times ey. Then clearly partial derivative of f with respect to x, keep the y constant, that means ex itself, ey constant. So that means it gives you back the same functions, and by the way all of these derivatives also turned out to be the same function xy. Awesome. Now let's move on. Example 3. Find all first partial derivatives of functions f equals to x sine of x square y plus y to the x. So let's begin the solutions. Let's take the partial derivative of f with respect to x. Keep y constant. So here we need to apply the product rule. So x derivative is 1. So just copy the second functions as it is and plus. Now first function x as it is, then sine becomes cosine x square y, and by chain rules taking derivative with respect to x, that means y constant, so 2xy. I hope this makes sense to you. And for the last term here, which is y to the x, we are taking derivative with respect to x, so y is constant. So then by formula we know the derivative of a to the x with respect to x is ax ln a. So now here is yx ln y. Similarly, the partial derivative of f with respect to y becomes x cosine x square y times x square plus xy x minus 1. So the last one is here. We are taking derivative with respect to y. So that means x is constant. Then we can apply the power rule for this one here. So x times y to the power x minus 1. I hope this makes sense to you all. Let's move on. Quick remark. For a function of 3 variables, the partial derivatives can be found analogously as in the 2 variable case by taking the other 2 variables as constant. So that means when you take a partial derivative of function of 3 variables with respect to x, take y and z constant. Similarly, while taking partial derivative of function of 3 variables with respect to y, take x and z constant. Similarly, when you're taking partial derivatives of function of 3 variables x, y, z with respect to z, take x and y constant. I hope the idea makes sense to you all. Let's move on. Let's do example 4. Find all the first partial derivatives of function of 3 variables f equals to x cubed yz square plus x e to the power z. Solutions. Let's find the partial derivative of f with respect to x. Take y and z constant. So here yz square constant, x cubed becomes 3x square, plus here the ez constant, x derivative with respect to x is 1, so simply ez. Similarly fy, similarly fz. I hope this makes sense to you all. Aside, we can easily find the second partial derivatives of function of 3 variable as well. Example 5. Find the first partial derivatives of f, which is given as integral x to y sine et dt. Solutions. We are using fundamental theorem of calculus. Let's take first partial derivative with respect to y. So x term is constant. Then this is simply we are simply replacing this t by the upper limit of this integrals y. So simply sine ey. And partial derivative of f with respect to x equals to, now here is y is constant, so I need to flip this integral to switch the sign, so minus integral y to x, then apply FTOC. It gives us simply replace t by this x, then minus sine ex. And here is again this derivative in this integral cancels, by the way. Awesome. Let's move on. The final remark. The functions ex times sin y is a harmonic function as it satisfies the Laplace equations fxx plus fyy equals to 0. Please make sure you got this. So with this remark, we finish this sections 14.3 partial derivatives. Thank you.